Welcome to Energy Talks, a regular podcast series with expert discussions on topics related to power system testing, data management, and cybersecurity in the power industry. Hello, everyone. My name is Scott Williams from the podcast team at OMICRON. This is the 6th episode of our special Energy Talks mini-series called Cybersecurity in the Power Grid, in which we provide you with a 360-degree view of how power grids can best safeguard their infrastructures from cyber attacks. In this episode, OMICRON cybersecurity expert Andreas Klien will be your host, and a special guest will join him to discuss the chances and risks of operational technology, or OT, in the energy and aviation sectors. So without further delay, welcome, Andreas, and thank you for hosting this episode.
Thank you, Scott. Hello, everyone, and welcome to the 6th episode in our Energy Talks Cybersecurity mini-series. My name is Andreas Klien, and I will be your host for this episode about aviation cybersecurity and the crossover to power grid cybersecurity and what we can learn from each other. I have been focusing on communication in the power grid for almost 19 years now, and 14 years of that time I've been focusing on cybersecurity in the power grid. And I'm responsible for leading the business area Power Utility Communication at OMICRON. Joining me for this episode is the renowned vulnerability researcher and firmware dissector, especially OT and critical infrastructure device firmware, as well as Vice President of Technical Research and Integration at aDolus, and 40 Under 40 Engineering Leaders Award winner, Brash.
Thanks, Andreas, for having me. It's great to be in a respected company. Those are really kind words. So I think the real pragmatic engineer in the room is actually not me. It's Andreas. He's in all conversations.
Thank you so much. It's an honor to have you here. And I just recently got to know that you've got this award, 40 Under 40 Engineering Leaders. That's very impressive. When did you get this award?
I think it happened during the dark years of COVID. I never fully figured out who nominated me. But truthfully, it's a pretty humbling award, especially when I'm not an engineer by trade. I'm not allowed to use that in my country. But I believe it's just the sound of being able to ask hard questions and go straight for the cause. And in some industries, this is kind of funny why it's an award. That's not exactly welcome. But here we are asking hard questions about energy, oil and gas, and aviation. So let's do this.
Let's do this. We had this idea for this episode when we met last time in Copenhagen at a conference. It was an industrial cybersecurity conference. And you mentioned so many interesting stories about cybersecurity in aviation. And so I have to admit, a bit of an airplane nerd. And so I had the idea, why not exchange some scary, creepy stories about cybersecurity in aviation and compare it to cybersecurity in the power grid? And maybe we can learn something from each other.
Yeah, absolutely. So in the aviation industry, I think what would be really interesting there to talk about is the word safe and unsafe. Because in cybersecurity, that's often a really convoluted term. People assume that my credit card data being stolen is an unsafe activity. And it's an event and it's negative. But unsafe in aviation is a very, very different thing. I've heard people call industrial cybersecurity and critical infrastructure is the industry where we're in the industry of making craters. That's kind of true for aviation for many cases. So unsafe, we have to be careful how we use that in the industrial world, in transportation being nonetheless, compared to, say, regular cybersecurity. So it's usually a lot harder to explain concretely why someone would need to halt operations or ground what is really just a flying mobile operational technology site or OT site, flying kilometers at over us. And versus you have something like cybersecurity unsafe, which is personal information, ransomware, and other things bringing down, batch manufacturing at sites. So those are very, very different definitions of unsafe. From a network point of view, in aviation, we're talking about airworthiness. And so if you start looking for words like airworthiness and flight systems on Google, you're going to have a very terrifying adventure. And when you make these claims, you have to be very sure. It's not like, let's just publish a CVE and it maybe will get tagged as controversial. That doesn't work on aircraft. You have to make very astute calls, as we probably know recently with the Boeing 737 MAX stores. And often the one thing to consider is that even the vendor is often unsure. What's scary about airplanes is you could have two planes built back to back, one after the other, and they completely behave differently. in theory, they have the same parts. They have, in theory, the same certified components, but there is subtle changes even with the same pilot. So just remember, when you talk about cybersecurity and unsafe, all of this has to factor in it. Every tail or every plane generates telemetry or is retrofitted differently. So when I think about scary things in the aviation industry, I think everything is so different, and you have these systems of systems. And so what can happen, bring back an airworthiness report, is that there was a heads-up display. I think it was in 2013, possibly 2009 from memory. And there's this Rockwell Collins heads-up display that could be plugged into this aircraft by default, but a second one was an option. They're both certified, both made for this aircraft. When they were plugged in on a certain aircraft and Wi-Fi was turned on, both heads-up displays would go blank while in flight.
Sorry, are these cool glass screens that you see in the Dreamliner cockpit pictures?
Yes.
That come down from the ceiling, something like this?
Yeah, or the dashboard as well. So usually you have a primary and a secondary pilot kind of arrangement, and some of the airlines that are a little more cheap or in other countries that are developing, they might not have both options. It's usually often added.
And you keep saying that over the last years, you call airplane a flying OT site, which is very interesting a way to see it. Flying OT network, which can be attacked, especially when it's on ground, but even in the air. And what is really interesting to me is that you also mentioned that the airplane behaves different. I thought that airplanes are mass produced, so that they behave the same because it's the same components. Are these different components, or what did you mean there?
Great question. So I'll step back 1 second on that. So when you buy an aircraft from the manufacturer, there's usually a set of standard reference specifications on how it's built. It'll have 2 Pratt & Whitney turbines on it. The avionics will be from, let's say, Honeywell for ground avoidance, those type of technologies. So in theory, all of the assembled parts are as the bill of materials would specify. Now there is adaptations here where the airline can actually add code on top of what was already provided by, say, Boeing or Airbus or Embraer. That's not a common thing that most people understand, is because it's done for different safety paradigms from the airline. It's done for different fuel economy, for those type of situations like flight and thrust logic. You have and then you have your typical nav plans, of course, but there's a bunch of other logic in there that gets it. And so, interestingly enough, if you're buying a plane from a manufacturer, its spec will be different. Now, what was interesting is I worked on a 7 project for Dreamliners and eventually for Maxes. And you would see the planes talking differently. And what you'd see systems failing. So let's say there's an extra entertainment system, the in-planes. That can be made from couple different companies, depending on how it was sourced at the time and who was changing hands. One day it's Thales, one day it's Panasonic. And you'll start to see logs show up saying, for example, we're running out of space or bad flash cell. You'll see behaviors where sometimes during the retrofits, their plate changed just enough. So you have like Aero, legacy technology Aero 1 combined with 2, and you'll see a slightly different behavior in the logs. The most scariest one I ever saw was a shell popping up. No one could tell me why that happened, what tool did it, or what. But planes, yeah, they do behave differently. They fly, and I'm sure to a pilot, maybe they can tell. But the systems themselves, there is little subtle differences.
But what you mentioned there with loading code later by the airline and this shell popping up, is this only in these non-critical entertainment system networks, or is this also deeper down?
So generally there's a model, and you can probably find references to it these days on the internet, but there's several layers, and it's done on a time-delimited bus. Think fault tolerant Ethernet, if you're familiar with that from the Honeywell technology side, where they shim in. Airplanes have a similar strategy. So when you see an Ethernet where you're like, ooh, no, you're probably not going to be able to talk on it unless you know how that protocol works. But there's these series of, let's say, rings, these layers, as you get closer to the avionics and the critical systems. Those are all separated, and they have a subscriber model as well. So there is a number of firewalls in between. But the fly-by-wire stuff, there's definitely some unique stuff hiding in there.
So what are other scary things you saw in airplanes?
Oh gosh. Pointing back to the airworthiness award kind of point, I'm more afraid of the RF attacks these days.
That is radio frequency.
Yeah. Yes. Yeah, radio frequencies. Whether you could refer to like Ruben Santa Marta's go point the radar dish Black Hat exploit, although I was involved somewhat in reviewing that, and some of it had truth and some of it did not at all. But that depended also on each airplane and each airplane operator. those things all apply differently. But the RF, most planes are not built to be shielded from the interior. They're built to be shielded from the exterior. And shielding is a weight. So that to me keeps me up every time. It's not so much like, oh, someone's going to go poison the entertainment system. It's not that. It's when someone's going to do something bad and bring on a high-powered amplifier on a plane.
So especially in that moment when they tell you to turn off all electronic devices, that would be a good point to turn on your software-defined radio, right?
Yeah. So I used to live on a landing path to a major airport. And when there was a certain type of cloud, and pardon me, I'm not a meteorologist, but there's a certain type of cloud that appears green. And it's very, very heavy. And it's just, you can see that all the planes are either going to have to divert to another airport, circle until the storm has passed, or they're going to land as fast as they can. The reason why I'm bringing that story up is that the land as fast as you can or take off as fast as you can is tied to that period where the most dangerous parts of operating a plane are when you're landing or taking. There's also, in those periods there, you have alternates. So it's not just the pilot with your typical avionics choosing, here's my runway, call it in. You have ultra high frequency data. You have GPS data. You have VHF you have all of these different communication channels. During landing and taking off is when they are the most important, especially if you have like a low cloud ceiling, right? You're operating blind. That's where I start to really panic is what happens when someone with SDRs puts them on balloons on the pathway, because they're not that far away from the aircraft at that point as the aircraft is coming down towards Grand Terra. But those are the areas where you already have very stressed pilots, bad weather conditions, and back to back. Like there's no room for error of double aisle jumbo jets coming down. That's where I started to get concerned is you're not causing a pure cyber event. You might cause an event by duplicating the operator's decision and stressing them out.
Yeah, that's also a common attacker strategy to have a minor cyber attack, which is confusing the operators to do severe mistakes. That is something which is imaginable also like all over OT in process control. There's always humans sitting in front of SCADA displays. And if they're reading the wrong numbers, they make the wrong decisions, right?
Yeah. Or they'll make the correct safe decision, press the big red button. It is prematurely being pressed.
Which is at least the financial damage, to say the least, yeah.
Yeah. So I think fun thing that Andreas and I had a great conversation about, I think when I met you about 3 years ago at an event.
We were in panel discussions together, yeah.
And I think one of the things we were talking about with rail was you have things like relays that are present in other industries that are not just rail. And while we're talking about aircraft and rail and maybe maritime shipping, it makes you wonder about how much of the devices are a shared commodity across all of these. And Andreas is a really good war story here because it comes around forking products and one getting attention in another. So Andreas, I saw this sort of with aircraft where I know components come from the industrial side, but have been produced under a different name for a different industry and probably share a code base. But that's a scary thing as well. What do we not know in the rail side?
Yeah, so there are automation components. I didn't know that they're actually used also in the aviation industry, maybe not in a plane, but maybe on ground, since it's also like automation functions there. There are these products which come from one industry, maybe automation industry, because that's the biggest one in volume. And then they're forked and relabeled for other industries. So there are automation components like PLC components used in the power grid industry, in substations, for example, in protection relays. So there's PLC modules used in protection relays, and then the protection relays are again relabeled for the use in railway. And they have different product names, sometimes even brands. There's a single heavily used protection relay is available under 3 different brands, an American brand and a French brand and a German brand, but it's all the same firmware running there. And in the railway, we have also the situation that they're relabeled because there are big railway networks which operate on a different frequency. So we have 50 hertz or 60 hertz, for example, usually in the normal power grid. But when it comes to railway, we have 16.7 hertz approximately, which is used in Central and Northern Europe only, but not all over Europe and definitely not all over the world. So you have some special products which have the same firmware, but maybe a different config file or slightly modified software, but labeled under a different label. But essentially the same components are used there and they share a lot of the vulnerabilities. And stress there, sometimes you cannot be sure if all the vulnerabilities are really covered there because it's such a niche device. So that is the point that we had there.
Yeah, and that's kind of one of my scary moments as well, as you fix it in one place, but it's wacko. It's very tough. So like, for example, on a Dream library, there's a certain LRU that's the same as a very large, very expensive DCS unit. So you see these shared components, but you never see a CVE for that avionic or the aviation equivalent of that.
Are there CVEs for aviation devices?
No. They usually go under airworthiness reports and quietly get hushed or fixed as a part of an SOP.
Okay. Fixing software for aviation must be really hard because much of the software you need to fully prove, almost mathematically prove and certify each line of code. And I've heard about several software bugs which were fixed by changing the hardware so that you don't need to patch the software because it's so expensive to patch the software.
Yes, there's a similar issue in medical devices as well. What constitutes a change? There's a lot of software-defined nature on it. So they will flip out software and hardware parts. Actually, software is treated like a part and it gets stored and signed and put on aircraft, although usually they don't verify the signing per se and enforce it. It's just done there because you might cannibalize an aircraft and need to move parts. But yeah, there's a substantial different way of proofing code and there's other different languages around it. Think Rust to even its predecessors like Ada. And those were all very scientifically proven languages, although Ada didn't really go far. But kind of talking about that masquerading, that's scary for a lot of people because a lot of features get left in. I guess the real enemy here is certification. Often you certify the same product firmware, but it has 10 different products in it, in theory, or different SKUs. That's a really kind of a scary thing because recently, as you might have known, there was a cybersecurity incident in Denmark that was publicized about. There's a lot of interesting conceptions about it, but the device that was used in there, and you'll see its presentation, this device allows out-of-the-box LTE, 3G Huawei modems. Now, it doesn't have that on the hardware BOM because, of course, you have risk through peripherals. So if you're in an environment where certain sanctioned companies are not allowed to operate, this is an interesting way because you have a threat model that you hadn't accounted for.
So the features are plugged in as USB, basically. And
yes,
they are not mentioned in any SBOM or anything.
No. And the scary part is that the drivers for these Huawei USB sticks are open source. So they're not created by the company itself. They're created by someone else. The function if you're building SBOM, you would just see Linux kernel. You might see that module. But the actual real driver logic code is on the Huawei USB stick. That would be generally they're mostly reprogrammable for various different carriers. So that's kind of a very scary thing for me because that's the risk. You've got a company focused on features that sell, and those features that sell will definitely help an operator, right? In this case, the use case most likely is, I'm a small company or a small town that has no money. I would like to have a router with a backup USB LTE gateway. That makes sense as a feature. It's cheap, but the problem comes in is that cheap feature will often get abused and compromise the entire security of the system. So circling back all the aviation into every industrial world, and there's some great material out there on CIE, but the biggest flaws I've seen are largely because they're related to human behaviors and capitalism in some way. So if you're someone in the business of risk, how do you engineer yourself out of this? And I guess that's a fun segue.
So the risk here causing the human error or the supply chain problem is capitalism. Or what did you say just?
Capitalism is like the root of all cybersecurity issues.
Yeah, well, in a way, that's true. Yeah, it's also the opponent of all security measures, right? Because it's an investment and it's time, and it doesn't really give you a lot of features if you're just improving the security. So essentially, it's always the opponent of making things secure.
Yes, the Ouroboros.
Yeah. So then another question which I have now, we are almost touching supply chain risks. How shall we identify risk in supply chains? You've been analyzing firmware for so many years now. How can we identify risks in the supply chain?
Yeah, so that's a really interesting area as well. When people say supply chain, what do we mean by supply chain? And there, the supply chain or a supply chain attack begin or end. So if you took, let's say, one of the other attacks, think of one of the Ukrainian attacks, and their accounting company got, their software got infected, and that was used as distribution mechanism, very similar to SolarWinds. Is the supplier the supply chain attack, or is the impact from start to finish calculating all of that? And that's where I'm not sure. And to identify the risks with this, there's a couple of different strategies, and really depending on if it's a hardware-related supply chain problem, is it a software-related one, or both? Is it a knowledge problem? Is it a creation versus distribution supply chain problem? There's all of these different areas, and Airfires is going to really get top on this on how there is no taxonomy. It's all of them, and we need to do more work on that as an industry. But in supply chain attacks, you have a couple different cases. Most people think of open source and that being kind of manipulated in. If you're an asset owner, how would I get visibility on that? And what would I do even if OpenSSL, this version of vulnerable OpenSSL is in there and we know that there's various groups attacking it? That's all tough. The real answer is, what can you do? Well, visibility is part of it, but you have to have the ability to take action on that. So if you know that you have devices with vulnerable agent components, you're going to have to revise your risk management strategy to then include defense in depth layers. Technological diversity, of course, does cost money, like anything does when you want to be robust, but that's generally the main strategy. So supply chain risk and dealing with those things comes down to not being entirely locked into a vendor, making sure that you have products that have long end of lives and the vendor is updating all of the pieces inside of it. Treating supply chain risk like third-party risk, those are all pieces here. And all of these relationships are so tied together. And then that even gets complicated by the world of business in supply chain, because that vendor is changing its names. The CDs don't match that product's rebranding anymore. Those are all aspects here. So I know it's a very tough question, Andreas. So I'll pass it back so we can focus just a hair.
So maybe a more general question for an overview for those listeners who are not so into aviation industry here. Could you give us a short overview? What would be the network structure of such a OT network around an airport and the plane being attached to it?
Yeah, great question. So in a very, very simple airport, something with only one or two doors to let passengers out onto the tarmac, you have a number of different systems there. So we will first think about it. Let's start like as a passenger walking in. Passenger walks in and there's these series of kiosks there to accept my suitcase, print my tickets. Maybe there's somebody at reservations. That's kind of one big that's one big part of this network here. That's kind of your DMZ. Obviously there's going to be some wireless around, but this is your main point of entry. Now, on this journey, you're actually just starting your IT-OT converged journey right there when you check in your suitcase. So as soon as your suitcase gets a tag, it's got a barcode on it, and it's going to go into the system from track mode from start to finish. Mm-hmm. Kind of after that, you're going to have some automated conveyor belts, some image processing type devices that push your suitcase everywhere it needs to go in the airport. There's, of course, going to be border control and X-ray scanners and those type of systems, but I'll leave that aside for a second. So once that suitcase goes all the way down and gets ready to be loaded aboard the aircraft, there's kind of a bit of an air gap there where your suitcase goes across and into the plane, but there's some barcode scanners along the way. And then you have this big plane sitting on the ground, weight on wheels. As you're thinking about that, okay, so we had an IT type system do reservations. We had a OT automated system getting a product from A to B. You have ticketing, which then is related to the gate on the plane. Because if you have a ticket and your suitcase is aboard the plane's supposed to not take off unless you're aboard it, due to a very terrible event that happened in Colombia, if I remember correctly. Then you have the other systems aboard the aircraft, which are then going to be talking to the air traffic management in the tower. So you have all of these different systems talking, but the real amazing thing is that your suitcase at the IT side can hold up the plane if the details are wrong. So that's kind of the first demonstration of a very connected thing. And then, of course, you have when the plane is in the air, all the systems that speak to it. And then when it lands in its reverse airport, in this destination airport, you have all of those different systems all talking and communicating. Even the plane is talking to the sky and telemetry is being streamed from it. You have radar things. So I truly think aviation is probably the most interconnected industry of them all, and probably one of the harder ones, but also one of the most safety critical ones too.
That's interesting. So in the power grid, the networks are not as interconnected. They're more like a bit of a tree structure where we have the control center at the top with, of course, auxiliary networks there for kind of IT services in OT. The control center would be like the tower commanding the plants and substations there. And then it's connected more top down from the control center downwards up until Purdue level 1, where we have the controllers and protection relays who are really doing something or protecting the equipment there. So that would be the structure there. And so the interconnectedness is not on that lower level, but definitely there's a lot of interconnections from the control center level and from these DMCs around it, which are also quite interconnected. If you just think about there's some smart meter data coming in. You have engineering teams who are working with data and configuration files for the devices. All of this needs to be exchanged even when you're down there working in the field. And these transient devices, the laptops of those engineers, they are one of the important attack vectors to attack the grid at the bottom level there. So we have maybe a bit of less interconnectedness, but there is always more connections than you might think there. So one example is that every time we're demonstrating or installing our intrusion detection system in power plants or in substations, on average, there are always 2 or 3 connections from outside networks, which are going with a permanent TCP/IP connection directly to a Purdue level 2 or Purdue level 1 device, a protection relay, a network switch on that level, maybe. And it's always funny how every team thinks that their connection is the only one that is there. So you have at least 2 or 3 connections always, like this. Every single time there are 2 or 3 connections down there. And every time the team who is guiding you there and opening the door for you, they think their connection is the only one. And then there is always one connection from the protection engineering team. There is one connection from the SCADA team to the control devices, automation and control devices. And the networking team has one for managing the Cisco switches or Siemens RuggedCom switches. And this connection also seems to be open permanently in many cases. And what was really interesting, what I saw there once, is that in one substation, we had the maximum was over 60 external IP addresses who had a permanent connection to the devices in that very large substation. So we had 60 connections where you need to discuss, is this really necessary? What do you need this for? Is this mission critical, or do you really want to accept that threat there? And in the same substation, we had the case that they had an interesting brand of protection relays there, and they had an old Samba server running. So you were able to drop configuration files directly into the directories of that Samba server. Not to mention that the Samba server also was pretty old, and there are a lot of vulnerabilities in this Windows file sharing server service for Linux. That is something that all the relays, 60, 70 of them, had this kind of scary, if you imagine this, because it was a huge substation for a major city.
Yeah, that's really common. I mean, whether it's Samba, you'll see the same thing. You'll see FTP drops on a lot of the older VxWorks stuff, even with their debuggers enabled, because it was left on as part of the board support packages. A lot of the really old relays and packs, they all have this. So you could definitely think about, if you wanted, you could drop your malware, or someone could leave something malicious on there, and the engineering software will pull it back into a green, more secure environment as well that you think is isolated. That's also something that's really common with a lot of the DCS devices, where they're all running, the primary and secondary servers are all Windows-based, and they will probably blindly accept any configuration given to it by a device.
Yeah, FTP is an old and insecure protocol, and if somebody sees an FTP server, they're afraid it should be there. It should at least be SFTP, as if that would be any better. But the point is that this FTP servers, everybody knows them, but those protocols which are native to OT are in many cases even more dangerous than an unpatched FTP server, or a patched FTP server, definitely. So we have the example of the 6150 MMS protocol, which is a protocol from around 1970 to 1980. It is an OSI protocol, which was then ported onto TCP/IP. So you don't have 7 layers, you actually have like 9 layers of TCP/IP plus OSI stacked on top to a skyscraper. And this is one example of a protocol which is also quite dangerous.
Yes, and some of its different dialects are also kind of dangerous. As we're speaking English, just because we speak English doesn't mean we understand each other the same way. And MMS also has some interesting flavors at some of the different layers as well that could lead you to places where had you been fuzzing or destructive testing, you would have found cases where your state machines break, not just for the power of the protocol and the devices it's communicating to, but just the protocol itself will have edges, very rough ones.
Yeah, we've been through that. Yeah, so I was working in the team where we developed a new 6150 client stack. So it's the MMS protocol client stack. And there we developed it from scratch, and then we released it as an update to a product which already had a big user base. So there were thousands of users already. We knew what we were doing, so we've really tested it extensively with more than a dozen of different devices from different brands from all over the world. And then when we felt really safe to release it, and we released it, we got many calls of people who complained that their critical protection relay crashed when our client stack connected to it. It was back in 2014, maybe. And the point was that not our client stack was behaving in the wrong way. It was behaving perfectly according to the standard, but the devices were not programmed with that client as a reference, so they did not expect that behavior. We tried to bundle some requests together to make it more efficient, and that stuff was not expected to the stack developers of those old relays there, and there were many devices failing. And what was really crazy is that, of course, nobody can patch the devices in the field, so we had to patch our client to somehow adapt to that so that we don't crash the devices. And sometimes it was really hard to not crash it. There are so many bugs and vulnerabilities in these implementations, it would be very easy to find something to crash the stack and essentially to crash the whole protection device. To fix this, we added like soft modes. Always when we detected a device like this, we started inventing things like an overcautious mode. And for some devices, we even had an additional mode, which we called internally a kid gloves mode. And we still use that. So even in all our products, when we detect behavior like that, in order not to trigger dangerous bugs, we are activating this gloves mode.
It reminds me of a bunch of unsafe architectures that humankind devised or created. So one of the things you mentioned was like, for example, crashing the stack. In old devices that were serial based, they only expected one speaker. And a lot of the old flow meters and things monitoring, let's say, water in very, low power type conditions run for years, many stuff like Honeywell mercury meters and stuff like that. They're not used to the cocktail party problem because they were designed in an era where physical access was the only thing possible. Scratch that, we have, serial TCP relays, our gateway devices that basically shuttle everything on, which is kind of what 61850 really was, is shimmed onto several different protocols. 104 and the others are the exact same way. But they weren't originally designed for such a multitude of network devices all speaking to each other. So there's all these different states that you can see on old devices, especially when you're fuzzing state machines. You will see that they were never designed for that very fast. But shockingly enough, in many of those cases that are singular, if you don't exit the communication correctly, the device will hang on a second one because it's the state machine again gets inferred and used in a wrong way. So a lot of these old protocols, they just weren't meant for testing, for one or more than 10 clients at once. There was no edge case saying, what happens if I go 10 plus one? It's just very, very common. Or what happens when someone pipelines two Modbus packet or payloads back to back to each other? Most testers never think to do that, but that was really common, and that was a normal behavior with serial. You do streamline and you pipeline your packets back to back. So when you talk about like unsafe architectures, it's mostly people just don't engineer to test in many cases. And we see that.
Yeah, especially when they always have the one kind of OT system in mind. And over the years, the product is used in different applications, and then suddenly other usage scenarios are possible. The products you're mentioning before with this bugs in the serial implementation, which are these, for example?
There's a couple good ones. So Honeywell Mercury devices, so they're part of the full Honeywell brand now. It's not the exact new model name, but a lot of the earlier ones were Windows CE based. There's other serial devices, flow meters that are part of, like, let's say, the Emerson catalog or Rosemont series. Those serial protocols often get pipelined over top of a TCP gateway, which then probably has OBC Classic as well, doing all sorts of fun DCOM, SMB related tasks as well. Yeah. These are just really common things, but they just don't, usually a lot of these devices and some of the VX Workspace ones, if you instantiate telnet connections to them, you really have to hang up or close the connection properly, because you will run out of the connection pool is dead. And in one device I worked on, which was a Bachmann MPC40, I think, which was stolen off the gray market from a freighter for controlling water on a freighter for ballast. That device, that if you didn't connect telnet correctly, it would crash the telnet server as well as other peripherals, and the only way to get it back was to reboot the device. So you have you can have non-malicious activities hanging your devices for you if you don't do destructive testing.
Yeah, it happens all the time. And I mean, in many substations with older devices, but still 61850 protocol based, a denial of service attack would consist of just 10 SYN packets. So you open 10 connections and then every other client is locked out. You cannot open another connection. So it's a denial of service with 10 packets.
That points to an interesting thing for people that are looking to try and get ideas of risk prevention. One of the most common and best places, I think, to look for that type of information isn't CDEs. It's actually the hardware errata notices that come from your vendor. So in some vendors, they're constantly doing change logs on what they're fixing in the product. And you'll notice there's often a lot of wording in there that points to a cybersecurity issue, but is not claimed as a cybersecurity issue. So for example, a Modbus packet with this range, with this code, causes the CPU to go into a halt. That's a big issue. That one's like, you just told me how to write my exploit code. Thank you very much.
Exactly, yeah.
But that doesn't come out as a CVE.
Mm-hmm. Because nobody reported it as a vulnerability. It was just reported as a bug.
Yeah. So I often look into those things, or the hardware notices, especially if I know the CPU. ARM doesn't like everybody doing this, by the way. There's tons of hardware errata. If you think Spectre is bad, it's nothing. There's all of these hardware notices if you want to stay up late at night. But those, you have nothing else to do. Yeah, but the engineering ones, that's where I like to look for some of the unsafe architecture, because you'll see it very fast.
That's a lot of internet, and it works cross industry, right? So reading the errata pages, and basically every crash that is mentioned there is also a way, in many cases, a buffer overflow exploit. So
exactly.
It's just not researched buffer overflow possibility is behind many of these crashes.
Yeah. And I like to use words like errata and engineering focused ones, because that's the majority of our operators and facility people. Many of them are trained in, mechanical engineering and electrical engineering. So when people say, "Oh, buffer overflow," what does that mean to me? Device stops working. Like when someone says watchdog, okay, that means device will reboot probably.
Mm-hmm.
I don't need that in my process. That's a bug I will fix. The security language or safety, reliability, or productivity of OT, you just have to adjust your vocabulary. You don't have to be a super geek and know the witchcraft, the magic of cybersecurity. You just need to be like, I think this means the device is going to do something weird. Okay, that's great. I'll fix that. This means that somebody could maybe get onto it with HTTP over versus having encryption over HTTPS. Do I really care? I do if I'm talking over the internet, over an insecure channel. But the one that says my device could accidentally crash, that's one you want to prioritize.
Exactly. Yeah, that's also the most frequent reason for patching in the power grid is actually because of bugs and crashes, and if certain configuration doesn't work, because patching because of security vulnerabilities is something they think twice about because it always brings you operational risk. But if you already have an operational problem, then it's close that you think, okay, let's update the firmware. And so that brings me to my final question is, do you have some recommendation of cross-industry best practices? So maybe we can summarize our findings here to define some benefits of best practices which can be taken from aviation to help securing the power grid?
Yeah, I think so. We're all kind of aware of the Purdue model and its lack or perceived value for security. And then you have the ISA 62443 models. Those are all great in their own right. And aviation actually has some very good ground system documentation that is almost identical to what you would see being recommended by the NIST special publication for ICS, as well as the ISA material. But the part that aviation does get a lot different is the reliance on things, let's for example, beyond GPS. The industrial world is only like relying on GPS for timing data. We probably shouldn't do that. That's not a good thing to do. A single channel, single source, not so good. Aviation has multiple channels for timing, for communication. That's something we probably should get back to, especially when we have forest fires and all sorts of different things occurring that might change the power grid as we know it to something far more unreliable. So we have something to think about there. Aviation is designed to be more robust, different conditions, and the grid is not. So there's a level there. Another great recommendation I think the aviation industry has been strong on pushing is not trusting transient laptops. Yeah, and your technicians and third parties, like they're very, very against that, and for good reason. I mean, most airports, they're not staffed by the airline. They're staffed by, contractors living in and out. The airport is not even a part of their airline's business, actually, really. Yeah. They're kind of just renting it. Knowing that and knowing what's in your hangars and what firmware is on an asset is crucial. So I think that's a lesson there that the aviation industry, we should be listening to. If we've got people going in and out of site, they should be using our laptops that we deem as clean and burn once they're used. That type of situation. Another really good case there that I think we should be doing, and aviation is very good at it, is assuming that aircraft have a timeline on them. So they don't buy an aircraft and say, I'm going to drive this thing into the... They don't do that. But we do that in critical infrastructure. I mean, they might sell that airplane to, airline B that's a cheaper one, and they'll use it for so many years and so forth. I see that in the energy industry, as it's changing hands. But they literally start thinking, this asset's getting close to its span. What should I do? Should I start thinking about buying another aircraft? And they start thinking about transitioning assets so they can still maintain a certain level of capability. We want to be resilient. And if we want to have energy and electricity and all the good things in modern society, we have to start thinking like that, which is assets will degrade, or one day you'll be left with one that's not worth anything to you. And you're stuck. What do you do then? And they think that way. It's far more resilient. Same with their predictive maintenance and controls. It's very different than what we were used to, where you can't even get a spare. Those are like 3 recommendation areas that I would say that are non-typical cyber, but just think differently and we'll see where that takes you.
Thank you, Ron. So I think we've done a good job in collecting some scary stories about bugs and vulnerabilities and attack scenarios for aviation, but also the power industry. Is there anything you would like to add in the end?
No, it's been an absolute wonder to be here, and to join Andreas and see him again is great. I didn't have to get on an 11-hour plane ride. So thanks again. And if anyone does have a chance to run into me in an event, or if they know I'm in town, please reach out to me and I would be more than thrilled to have a beverage with you.
Well then, thank you. And in this case, I hand over back to Scott.
Thank you, Andreas and Ron, for this informative discussion, and a big thanks to our audience for listening to this episode of Energy Talks. We always welcome your questions and feedback. Simply send us an email to podcast@omicronenergy.com. Omicron has several years of experience in power system testing, data management, and cybersecurity in the power industry, and offers you the matching solution for your application. For more information, be sure to visit our website at omicronenergy.com. Please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.